Welcome to phase 3 of our series. We're now diving into transfer architectures and evaluation. Today's focus evaluation metrics for LLMs.
Evaluation is crucial because it tells us whether our models are actually improving and how they compare to each other.
Let's start with the most fundamental metric perplexity. What is it?
Perplexity measures how surprised the model is by the test data. It's the exponential of the average negative log likelihood of the tokens.
In simpler terms, if the model assigns high probability to the actual next tokens, perplexity is low. If it's constantly surprised, perplexity is high.
Lower perplexity means better language modeling. A perplexity of 20 means the model is on average as confused as if it had to choose uniformly among 20 possible tokens.
Perplexity is useful for comparing models on the same dataset, but it doesn't directly tell you about downstream task performance.
Right. A model can have low perplexity but still struggle with specific applications.
That's why we use task specific evaluation metrics. Let's talk about question answering.
For QA tasks, the most common metrics are exact match and F1 score.
Exact match is binary. Does the model's answer exactly match the reference answer? It's strict, but sometimes too strict.
F1 score is softer. It treats the answer as a bag of tokens and computes the harmonic mean of precision and recall.
Precision is what fraction of the model's answer tokens appear in the reference. Recall is what fraction of reference tokens appear in the model's answer.
F1 balances these two. It gives partial credit for overlapping answers, even if they're not identical.
For text generation tasks like summarization and translation, we use different metrics.
BLU is a classic metric for translation. It measures n-gram overlap between the generated text and reference translations.
VLU computes precision for anigrams, bigrams, trigrams, and fourgrams, then combines them with a brevity penalty to discourage overly short outputs.
Rouge is similar but designed for summarization. It measures recall-oriented n-gram overlap.
Rouge 1 uses anigrams, Rouge 2 uses bigrams, and Rouge Dal uses longest common subsequence.
Material is another metric that considers synonyms and stemming, making it more flexible than simple word matching.
But these n-gram metrics have limitations. They don't capture semantic similarity well.
Two sentences can mean the same thing with no word overlap, or use the same words but have different meanings.
This is where embedding based metrics come in. BERT score computes similarity between token embeddings from a pre trained model.
BERT score aligns tokens from the generated and reference texts based on their contextual embeddings and computes precision, recall, and F1.
This captures semantic similarity better than n-gram overlap.
For broader capabilities, we use benchmark suites, collections of diverse tasks.
MMLU, or Massive Multitask Language Understanding, tests knowledge across 57 subjects from elementary math to professional law.
It's multiple choice, so evaluation is objective. Models are tested on their ability to select the correct answer from options.
Big Bench is another large collection, hundreds of tasks designed to probe different capabilities.
HELM, the holistic evaluation of language models, goes beyond accuracy to measure things like calibration, robustness, bias, and efficiency.
Let's talk about some specific reasoning benchmarks. HELASWAC tests common sense reasoning with sentence completion.
PIQA, or physical interaction QA, tests understanding of physical common sense.
Wino Grande tests pronoun resolution, which requires understanding context and sometimes world knowledge.
These benchmarks try to measure genuine understanding rather than pattern matching or memorization.
For code generation, we have benchmarks like human eval, which gives the model a function signature and docstring and evaluates whether the generated code passes test cases.
MBPP, or mostly basic programming problems, is similar but with simpler tasks.
These are evaluated by actually running the code and checking correctness, a form of execution based evaluation.
Now let's talk about human evaluation, which is often considered the gold standard.
Human evaluators compare model outputs based on criteria like helpfulness, harmlessness, honesty, and coherence.
Pairwise comparison is common. Show humans two model responses and ask which is better.
These comparisons are aggregated into rankings using systems like Elo ratings borrowed from chess.
Human eval is expensive and time consuming, but it captures qualities that automated metrics miss.
There's also human preference evaluation, where people don't just judge quality but indicate their actual preference for real world use.
The challenge with human eval is consistency. Different evaluators might have different standards.
And humans can be biased toward longer responses, certain writing styles, or responses that confirm their expectations.
Another evaluation approach is using LLMs to evaluate LLMs.
You can prompt a strong model like GPT-4 to judge the quality of another model's outputs.
This scales much better than human evaluation and correlates reasonably well with human judgments.
But it introduces its own biases. The evaluator model's preferences might not align perfectly with human values.
Let's talk about evaluating safety and robustness.
Toxicity metrics use classifiers to detect harmful, offensive, or toxic language in model outputs.
Bias audits test whether models exhibit demographic biases. Do they produce different quality outputs or stereotypical associations based on gender, race, or other attributes?
Adversarial evaluation tests robustness. Can slight perturbations to the input cause the model to fail or produce harmful outputs?
Red teaming involves actively trying to make the model misbehave, attempting jailbreaks, prompt injections, or edge cases.
These evaluations are crucial for safety but challenging because the space of possible attacks is enormous.
Another important dimension is calibration. Does the model's confidence match its actual accuracy?
A well calibrated model should be 90% accurate when it reports 90% confidence.
Calibration can be measured by looking at the relationship between predicted probabilities and actual correctness.
LLMs are often poorly calibrated. They can be overconfident or underconfident.
There's also the question of what to do about hallucination when models generate false information confidently.
Factuality benchmarks test whether models generate accurate information about the world.
Groundedness measures whether the model's response is supported by provided sources, which is important for retrieval augmented systems.
Now, an important issue data contamination. If test examples appear in training data, evaluation is invalid.
Some benchmarks have been solved not because models truly understand the task, but because they memorized examples.
This is why new benchmarks keep being created and why some evaluations use private test sets.
It's also why measuring contamination is important, checking for n-gram overlap between test data and training data.
Let's talk about interpretability and analysis.
Probes are small classifiers trained on model activations to test whether the model has learned certain concepts.
For example, you might train a probe to detect whether the model's internal representations encode part of speech information.
If the probe succeeds, it suggests that information is present in the model, though it doesn't prove the model uses it.
Attention analysis looks at which tokens the model attends to, giving insight into its decision making.
Attribution methods like saliency maps or integrated gradients identify which input tokens most influence the output.
But interpretability is still limited. These models are complex and we don't fully understand their internal mechanisms.
So, to recap, Perplexity measures language modeling quality, exact match and F1 evaluate QA, BLU in Rouge evaluate generation, benchmark suites like MMLU and Helm test broad capabilities, human evaluation captures qualities metrics miss, safety and robustness require specialized evaluations, and contamination is an ongoing challenge.
Next episode, we're diving into challenges in LLM development, the problems researchers and engineers face when building these systems.
Thanks for listening.
Until next time, keep learning and stay curious about AI.